Okay, here we have the true-false section from previous midterm 1. And so the first one says the following matrix is in row echelon form, true or false. So how do you determine that? First step, you got to identify where your pivots are. So those are just the first non-zero entry in each row. And after that, you look through the criteria. So you say, are the pivots going in the top left of the matrix to the bottom right? Yes, they are. And then are there zeros below all your pivots? Yes, they are. And if we had a row of all zeros, it would have to be at the bottom, but we don't, so we're fine. So this meets all the criteria for being in row echelon form. So we say true. Okay, the next true-false question. If A is a 2 by 3 matrix, then AX equals B can have a unique solution. And so with these kinds of questions where it gives you a constraint on the size, the dimension of your A matrix, I like to kind of sketch it out. So what does a 2 by 3 matrix look like? Well, it's rows by columns. So 2 rows, 3 columns. So these dashes just represent some number. And then for AX equals B, if I wanted to represent that matrix equation as one augmented matrix, you would put your B in the augmented column. So here's your 2 by 3 A matrix, and then you put B in the augmented column. So now we've represented it in an augmented matrix. And we want to see, can we have a unique solution? So if you have a unique solution, that means that you have no free variables, remember? So is it possible to have pivots in every unknown variables column? Well, what's the most amount of pivots you could have? You could have a pivot here and you could have a pivot here, but since there's more columns than rows, it's impossible to not have free variables. So you're guaranteed to have a free variable, in which case it's impossible to have a unique solution because free variables imply that you have infinitely many solutions. So this one's false. Okay, then the last true or false, if A is an m by n matrix, then the solution set of AX equals B is empty, or it is a span in Rn. Okay, these are the kinds of questions that a lot of people say give them anxiety. They read it and they're just overwhelmed. They don't even know where to start. So my advice to you is just take a deep breath. I mean, you got more time than you think. Just think it through and play around with what it tells you, and eventually you'll come to the right answer. So for me, the first thing that jumped out at me was this Rn here. And a lot of times the true-false problems will get you by saying like Rn when they meant to say Rm. So that's the first thing that I would check and see if that's correct. So it's saying the solution set would be in Rn. So to determine if that's true, we have to think what dimension does these x vectors live in? Because the collection of all the x vectors that satisfy AX equals B is the definition of the solution set. So we just have to see how many entries does the x vector have. So to do that, we have A, which is m by n, times x is equaling some B. And so how many entries does x have to have? Well, if you remember, how do you do a matrix times a vector? Here's some matrix times some vector. And you compute this by doing a linear combination of the columns of the matrix where the weights of the linear combination are the entries in the vector. So this would look something like 1 times 1, 3, plus 2 times 2, 4, right? And so if you notice, you have to have the same number of entries in your x vector as columns in your A matrix so that this linear combination is defined, right? So if A is m by n, that means there's n columns, which means x has to be in Rn, right? It has to have n entries. So you say x is an element of Rn, or you just say x lives in Rn. So that's actually right. So it says the solution set would be in Rn. So that part's true. But the part that actually will make it false, and you'll see why in a second, is that it says the solution set has to be a span in Rn, and that's not necessarily true. So to understand this, there's this theorem, which hopefully should make some sense to you, which says that the zero vector, you could just say zero vector, is always part of a span. So remember, span is just the collection of all the linear combinations of some set of vectors. And the theorem says that zero vector is always part of that span. And the reason for that is because a general linear combination, if you remember, looks something like this. Some constant times a vector plus another constant times another vector, dot, 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 for however many vectors you have. And if you just pick 0 for all your constants, then just like that, you get the zero vector. And since the span of these vectors would be all the possible linear combinations, by picking 0 here, you're guaranteed to have the zero vector as an output, and so zero vector is part of the span, always. And so we just have to see if the solution set is a span, that means the zero vector would have to work as your x vector here. And if b isn't the zero vector, then that wouldn't be true. Because if you have a times the zero vector, then that equals the zero vector, right? Think about this. If you had zeros here, you would do this linear combination where the weights are 0. And so if b is some non-zero vector, like, I don't know, 1, 2, or 0, 4 or something, then a times the zero vector would not satisfy that. And so 0 wouldn't be in the solution set. And so the solution set wouldn't be a span, because spans have to have the zero vector. So for that reason, the solution set is not necessarily a span, so you say false, because it's not always true.